So we were discussing the topic haloalkanes and haloarenes. Okay, so in the previous class, we have discussed about the substitution reactions. Okay, SN1 SN1 mechanism. Then we have seen what is SN2 mechanism. So based on that also, we have solved some MCQs. So today we are going to start with the topic that is okay. We are going to study the stereochemistry. So we are going to study the stereochemistry. So we are going to start with what is optical isomerism. Okay, for optical isomerism, for this phenomena to occur, what are the necessary conditions? Okay, what are the necessary conditions for optical isomerism to occur? Firstly, the compound must be having a chiral or asymmetric center. Okay, what do you mean by chiral or asymmetric carbon center? That means the central carbon atom should be linked to four different groups. Okay, they should be linked to four different groups or atoms. So when the carbon atom should, if it is linked to four different groups or atom, then it is said to be a chiral. Okay, it is said to be chiral or asymmetric. What it is said to be chiral or asymmetric carbon. Okay, so this is the first condition. So this is the first condition for the compound to show optical isomerism. So chiral. Okay, so what do you mean by chiral? Chiral means when it is attached to four different group atoms. Okay. Then second is the mirror images should be non-superimposable. The mirror images should be non-superimposable. Okay. Means what? Suppose I've taken my two palms now here. Now this is what this one hand is the mirror image of the other hand, right? So these are the mirror images. Now if I keep one hand on the other hand, okay, on the other palm, sorry. So will the thumb, is your thumb coinciding with the thumb of the other hand, palm? No, right? So this is called as non-superimposable. They are the mirror images, but these are non-superimposable. When you keep one above one, okay, so these are said to be non-superimposable. So the mirror images, they must be non-superimposable, and these non-superimposable mirror images are called as enantiomers. Okay, and these are called as what? These are called as enantiomers. So this is the optical activity. Okay, what is this? Optical isomerism. So these are the necessary condition. That is optical, first compound should be chiral. Okay, and the second one, they should be non-superimposable. Okay, they should be non-superimposable mirror images. Okay. So next is what is chiral carbon. So we are going to see the important points, okay, in the stereochemistry of our chapter, okay, of this compounds. So the what is chiral compound? Okay, what do you mean by chiral compound now? Yes, chiral carbon. So as I said, the carbon atom, when it is attached to four different groups, okay, when it is attached to four different groups or atoms, then it is said to be a chiral carbon. It is said to be what? It is said to be chiral carbon. Okay. Now this is the compound you can see here. So this is okay. So this is a compound, and they have taken the mirror image. So this is D isomer, this is L isomers. They have taken a mirror image. So if I keep this image on the another, will it be superimposable? No, it is non-superimposable. So these are called as enantiomers. Okay. So the compounds, when it is attached, when a carbon atom is attached to four different groups or atom, then it is said to be chiral carbon. And if it is non-superimposable, then it is called as what? It is called as enantiomers. Okay, it is called as enantiomers. So we'll go for the next one. So next is racemic mixture. What do you mean by racemic mixture? What do you mean by racemic mixture? So it is a it is a equimolar mixture of two enantiomers. Okay, it is a equimolar mixture of two enantiomers. So that is if you have a plus lactic acid and minus lactic acid. So 50% of plus lactic acid and 50% of minus lactic acid. So when these, okay, when they are present in equal amount, that is 50 and 50, okay, then it is these are mixed together. Okay, when equal amounts of plus lactic acid and minus lactic acid, they are mixed together, then what we get? We get plus and minus lactic acid. Okay, then these racemic mixture is always optically inactive. These are always optically inactive. So plus and minus, okay, what will happen? There will be zero rotation. Plus means what? It will go in clockwise. Okay, it will move to right side. And minus means what? The molecule will move to left side. Plus and minus, when plus and minus they are present in equal, what will happen? They will cancel each other and there will be zero optical activity. Okay, this gives rise to something called as racemic mixture, racemization. Okay, next is mesoisomer. Okay, what do you mean by mesoisomer? You can see this compound. Yes, so this is a compound. So you can see the carbon. So what is the activity here? So the carbon, it is chiral carbon. Why it is said to be chiral? As I discussed, chiral means what? This is a chiral carbon. So these are attached to four different groups. Yes, these are attached to four different groups. So thus this is a chiral carbon. Now the second carbon here I'll consider. Okay, it is the same compound. So now we'll consider this. So these are also attached to four different groups, right? So this is also a chiral carbon. Okay, so there are two chiral carbons. Okay, so a molecule when it is containing a chiral carbon atom, but there is a presence of plane of symmetry. So when you put a mirror image, is the half molecule equal to other half? Yes. So it is having a plane of symmetry. So when you are having a molecule which is having a chiral center, okay, chiral carbon atom, but with a plane of symmetry in this molecule, then it is said to be what? Then, okay, then it is said to be a mirror isomer. That is a mesoisomer. Okay, so a molecule containing okay, so molecule when it is containing chiral carbon, okay, but having a plane of symmetry. So if I put a plane of symmetry here, so the half of the molecule will be what? It will be half of the other. Okay, so this is the chiral carbon. Okay, so this is a meso isomer. So this is both are optically inactive. Okay, these are optically inactive. So we'll see some questions now. So which of the following compounds is non-active? That is not chiral. Not chiral means what? They will, not chiral means all the carbon atoms are not same. Chiral means what? Chiral means all are having different atoms. Okay, suppose different groups or atoms are present. Okay, now which among the following is not chiral? Means at least one will be same. Yes, try to write the structures and let me know the answer. Yes, write the structure and check how to write. Okay, I'll write the structures, then you can answer me. 1-chlorobutane. Okay, 1-chlorobutane. Butane is what? CH3, CH2, 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 and Cl. So this is 1, 2, 3, 4. Is it a chiral carbon? Okay, is it chiral or not? Then 2-chloropentane. So CH3, CH2, CH2. This will be CH, Cl, and this will be CH3. 1, 2, 3, 4, 5. So it is 2-chloropentane. 1, 2, 3, 4, 5. Okay, so this is 2-chloropentane. So let me know. Then the next one is 3. What is that? 1-chloro, 2-methyl pentane. Okay. Third structure, 1-chloro. So it will be CH2 Cl, then 2-methyl. So I'll place a CH3 here. This will have 1 and pentane. So 1, 2, 3, 4, and 5. Okay, so this is the C, this is A, this is B, and I'll write the D structure. 3-chloro. So 1, 2, 3, 4, 5. So 3-chloro, 2-methyl. So this is 2-methyl. Okay, and 3-chloro. So 1, 2, 3, 4, 5. 2-methyl, 3-chloro, pentane. So CH3, CH2, CH, CH, and CH3. Yes. See now, which is a okay. Khadija has answered it as D. Darshan has answered it as A. What about others? Okay, Nagaratna C. They have asked what? Not chiral. First, understand the meaning of chiral. Chiral means what? A carbon having 4 different atoms. Carbon having 4 different groups or atoms. Okay, it is said to be a chiral. Now this carbon has 4 different groups. Okay, now what they have asked? They have asked which is not chiral. Means what? All the 4 atoms are not different. Any one will be same. Okay, you have to tell. Okay, you have to check for that compound. Okay, which is not having all the 4 atoms or the groups different. Yes. What about others? I've got 3 answers. D, A, and C. What about others? I have told you the meaning of what is chiral. Okay, what is I'll just see here. I'll just expand it more clearly. Okay. Now here it will be CH H. Now here it will be what? CH. Here it will be what? CH. CH. Now here. Hmm. Yes. So here now these are all having same atoms, right? So these are not chiral. Now this is also having 2 same atoms. So this is not chiral. This is not chiral. Okay, this is not chiral because hydrogen atoms are same in all the case here. Okay, there at least 4 all the 4 atoms should be different. Okay, attached to that carbon should be different. Now in this case, this is a chiral, this is a chiral, this is a chiral. See this carbon. So this is one atom, this is another, this is second, this is fourth. Okay, so this is a chiral compound. Okay, now here you see for this carbon, these are 2 same. So this is not chiral. Then 1, then 2, 3, and 4. So this is chiral carbon. Okay, so this is also a chiral compound. Now here 1, 2, 3, and 4. So this is chiral compound. Then here 1, 2, 3. So this is not, but this is also a chiral compound. Now, what they have asked, which of the following is not a chiral compound? Okay, so this is chiral, this is chiral, this is chiral. So this is not chiral. So it is option number A. Understood? Chiral means what? All the 4 atoms, okay, of that carbon which is attached should be having 4 different groups. Okay, so the carbon should be attached to 4 different groups or atoms. But here you can see in B, C, and D, okay, there is at least one chiral center. But in A, there is no chiral carbon. So A is the answer. They have asked not chiral. Okay, so read the question properly and then you have to search for the answer. Next one, which of the following has a meso isomer also? Okay, which of the following will have a meso isomer also? So, which will be having a meso isomer? 2-chlorobutane. I'll write the structure CH3, CH2, CH, Cl and CH3. 1, 2, 3, 4. Okay, butane. So 1, 2, 3, 4. So if I write the structure, is it so for mesoisomer, what is the condition? It should have a chiral carbon and it should have a plane of symmetry. Okay, plane of symmetry. So these are the conditions for mesoisomer. Fine. So do it, is it is having a, is it having a chiral carbon and plane of symmetry? Yes, see whether the molecule, if I divide the molecule here, okay, I'll write it again more clearly. So C, H, H and H. So if I divide this molecule, if I put a plane of symmetry, is it similar on both the side? No, right? So this is not a mesoisomer. So this is not a mesoisomer, the first one. Okay. Now we'll go for second one. 2,3-dichlorobutane. 2,3-dichlorobutane. How it is? 2,3-butane. So it will be C 2,3-dichloro. So here also one will come. Then 2, 3. Here also one will come. And here CH, H, H. So this is one carbon, second, third, and fourth. So if I divide here, okay, if I put a plane of symmetry here, yes, is it isomer? Yes, it is a mesoisomer. So option number B. Okay, option number B is the correct answer. So that is option number B, that is 2,3-dichlorobutane. It is a mesoisomer. Understood? So for mesoisomer, the condition that is that it should have a chiral carbon and it should have a plane of symmetry. Okay, it should have a plane of symmetry. So we'll go for the next one. Out of the following, the alkene that exhibits optical isomerism. So which of the following alkene should show optical isomerism? Yes, for optical isomerism, what are the two conditions? It should be having a chiral carbon. And second is what? Non-superimposable mirror images. Okay. Non-superimposable mirror images. So out of the following, the alkene that exhibits optical isomerism is what? It is a chiral carbon. Okay. Or a non-superimposable mirror images. So we'll see now which of the following will exhibit that property. 3-methyl, 1-pentene. Okay. Pentene means what? 1, 2, 3, 4, 5. Pentene. Okay. At 1, it will be CH2, CH3. So this will be CH3. Okay. So this is the alkene which is exhibiting optical isomerism. For optical isomerism, it should have a chiral carbon. Just see which is having a chiral carbon. So this carbon will check 1. Okay, this is second atom, this is third, and this is fourth one. Yes, all the 4 different are groups are different. So this is condition is satisfied. Second is what? If you put a mirror image, will it be superimposable? Yes. Okay, it will be superimposable. So the alkene which exhibits optical isomerism is option number A. Okay. So option number A is the right answer. So if I go for 2-methyl 2-pentene. So 2-methyl 2-pentene, I'll write the here only. Okay. 2-methyl 2-pentene. 2-methyl. So it will come here. 2-methyl. Okay, now you see whether it is having any optical chiral center. First you see 1, 2, 3. So these are same. Here you check one, only one. Here also one. Okay, same atoms are there. Okay, so this is not, so it is not having a chiral carbon. Okay, for this now 3-methyl 2-pentene. So 3-methyl 2-pentene, 1, 2, 3, 4, 5. Now 3-methyl, add 3-methyl and 2-pentene. So 1, 2. This is 2. Now I'll write CH3, then H, then this is CH2, and this is CH3. So 1, 2, 3, 4, and 5. Okay, so this is 5, that is 3-methyl 2-pentene. Now you check 1, 2, this is not a chiral carbon. This is also not a chiral carbon. So first condition is not satisfied. Okay. So it is not having a chiral carbon center. Now we'll go for the fourth one. Okay. So this is also wrong. We'll go for the fourth one now. So for optical isomerism, there are two conditions. First is what? We have to check whether the compound is having chiral carbon, and second condition is that it should be non-superimposable mirror image. Now we'll write pentene again. 1, 2, 3, 4, 5. So 1 pentene. So again CH2 here, double bond will come, and 1, 2, 3, 4. So add 4, 4, 4 methyl. Okay, now you check 4, 4. So 1, 2, 3, 4. 4, 4 methyl, 1 pentene. Okay, so here also we are not having any. Okay, so the answer is A only. Understood? Like this, you have to solve for the structures. We'll go for the next one. How many chiral carbon atoms are present in 2,3,4 trichloropentane? So I'll write the structure of 2,3,4 trichloropentane. So pentane 1, 2, 3, 4, 5. 1, 2. So 2, 3, and 4 chloro. Okay. And rest all will be CH3 group. So H, 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 and CH3. Okay, so how many chiral carbon atoms are there? We'll check with this carbon. So one atom, 2, 3, and this is fourth one. So this is a chiral carbon. Okay. Now we'll check for the second one. 1, 2, this is third, and this is fourth one. Yes, these are different. No, these are same, right? CHC, HCl, CHC, CCl. So this is not a chiral carbon. So this is restricted. Okay, this is not a chiral carbon. Second one is not a chiral carbon because it is same. This molecule, okay, and this half is same. So this will be all the 4 atoms should be different, right? So here this is not chiral. Now next is we'll check for this one. Okay, so 1, 2, 3, and this is fourth one. So this is also a chiral center. So there are 2 carbon centers. Okay, so option number D. Understood? So you have to check for the carbon centers. We have to check for the carbon centers. So how many carbon centers are there? 2 carbon centers. This one and this one. So or chiral carbon means what? Or carbon carbon is what? 4 different groups or atoms should be attached to the center carbon. Okay, so this is the meaning. Understood? So now we'll go for the next one. The number of optical isomers of the compounds. So one compound is given, that is CH3. I'll just write it more elaborately. Okay. So CHBr. I've written the complete structure here. Okay. Only thing I've written the complete structure. So the number of optical isomers of the compound CH3, CHBr, CHBr, COOHR. So number of optical isomers. Number of optical isomers can be calculated as 2 into n. Okay, 2 raised to n. So here you have to first check the chiral centers. Okay, first check the chiral centers. So this is one different atom, 2, 3, and this is fourth one. So this is a chiral carbon. Next we'll go for this carbon. So 1, 2, then this is a third, and this is a fourth one. So this is also a chiral carbon. Then we'll check for the this one. So 1 and 2, these are same. Okay, so this is not a chiral carbon. So there are how many chiral carbon are there? There are only uh, so there are only 2 chiral carbons. So 2 raised to n, 2 raised to 2. N is nothing but number of chiral carbons. So it will be 2 into 2. So that will be equal to 4. So the number of optical isomers obtained from this is, okay, it is what? It is 4. So it is option number D. So what is N? N is the number of asymmetric centers. Okay, asymmetric carbon atoms. N is nothing but this N. It represents the number of asymmetric carbon atoms. I hope this is clear. So whenever you want to find out the number of optical isomers, how you have to calculate? 2 raised to N. N is what? N is your asymmetric carbon atoms. Okay, it represents your asymmetric carbon atoms. Meso compounds do not show optical activity because A, they do not contain chiral carbon atoms. B, they have non-superimposable mirror images. C, they contain plane of symmetry. D, they do not contain plane of symmetry. So why they do not show optical activity? We said that meso compounds are optically inactive. They are optically inactive. Why they are said to be optically inactive? Can you give me the reasons? Okay, why it is said to be optically inactive? What is the reason from this? What is the reason from this? There are 4 options. Please go through the options and let me know which is a suitable answer for that. Why it is not showing optical activity. What does meso compounds contain? Meso compound contains a plane of symmetry. So due to plane of symmetry, okay, due to plane of symmetry, suppose this is a molecule. Okay, suppose I'm just giving you example. Okay, so what will happen? The half of the molecule will be cut by the other half. So this will be, okay, so this will cancel the other half. So because of plane of symmetry, this is optically, they do not show optical activity. It is optically inactive. So option number C, that is they do not contain, they contain plane of symmetry. So because of plane of symmetry, they do not show optical activity. Okay, so this is the correct answer. Yes, optical activity. Good. Okay, so we'll go for the next one. What are aryl halides now? So aryl halides, so we have completed some of the concepts from the stereochemistry. Okay, now we'll go for aryl halides. So what are aryl halides? In this compounds, the halogen is linked directly to the carbon of the benzene. Okay, so we know that the halogen is linked to what? It is linked to the carbon of the benzene. So this is the aryl halide. Now, first we'll see the electrophilic substitution. So what we are going to see? We are going to see the electrophilic substitution reactions of aryl halides. Okay. So first is what they have done, toluene. Okay, toluene, they have reacted. So this is a halogenation. So toluene, when it is reacted with X2, okay, in the presence of Fe, that is iron, in dark conditions, it obtains orthohalotoluene and parahalotoluene. What is obtained? It is obtaining orthohalotoluene and parahalotoluene. So iodo derivatives cannot be obtained by direct reactions with iodine as the reaction is reversible. So here you can do this reaction with Cl, okay, Br, etc. But you cannot do with iodo compounds because the reactions will be irreversible. That is, it is reversible. You get back the reversible. Okay. So that is C6H5I plus HI. So this is. Okay, so when you react the benzene with iodine, it forms iodobenzene. Okay, so this reaction is reversible reaction, so we cannot do it with the iodine. So iodo derivatives can be prepared by reaction. So how this iodo, if you want to prepare iodo derivatives, then how we have to prepare? We have to prepare by reaction which is carried out in the presence of oxidizing agent. Then we have to use a oxidizing agent. So here the oxidizing agent is what? HNO3, that is your nitric acid. So HNO3 is the oxidizing agent. So iodo derivatives can be prepared by reactions, okay, in the presence of oxidizing agent. Here the oxidizing agent, what it does, it oxidizes the Hi into I2, okay, iodine gas. Iodine gas, which is, okay, so here it is -1. From -1, it is going to zero oxidation state, okay. Then second point, aryl fluorides. Now, what about fluorides? If you want to prepare aryl fluorides, okay, aryl fluorides cannot be prepared by direct fluorination because of the high affinity of fluorine for hydrogen, and the reaction is very violent. Okay, so these are some of the conditions for the halogenation, that is about iodine and fluorine. Chlorination, bromination can be possible. For iodine, you have to use, if you want to prepare iodo derivatives, you have to use what is that, oxidizing agent. And for fluorination, you cannot obtain by direct fluorination, okay, because of high affinity. So aryl fluorides cannot be prepared because of high affinity of fluorine towards the hydrogen, and this reaction is very violent, okay. Next is from diazonium salts. Okay, what is diazonium salts? Diazonium salts are, so this is a diazonium salt. Okay, this is a diazonium salt, that is N2Cl. So this is a benzene diazonium salt. So what is, how do you convert benzene diazonium salt? For that you have to take aniline. So aniline will be a starting product. So this aniline you have to treat it with sodium nitrate. Okay, sodium nitrate at 0 degree to 5 degree Celsius in the presence of concentrated HCl. Okay, you obtained what is that? You obtained the diazonium salt. You obtain what? You obtain diazonium salt. Okay, so these are the reaction conditions. So aniline is converted into benzene diazonium salt. Benzene diazonium chloride. Okay, salt means in the presence of chloride, right? So it will form a salt. So now this benzene diazonium chloride, okay, it will undergo several reactions. So we have to first convert aniline into benzene diazonium chloride, and this further is treated with different reagents. So if you treat it with copper chloride, okay, CuCl, cuprous chloride, not copper, it is cuprous chloride. Why? Because the Cl is in +1 state. Okay, cuprous chloride. Cuprous chloride, when it is treated with cuprous chloride, you obtain benzyl chloride. What is obtained? Benzyl chloride is obtained. So benzyl chloride is obtained. If you treat it with cuprous bromide, what is obtained? What is obtained? Benzyl bromide is obtained. What is obtained? Benzyl bromide is obtained. If you treat it with potassium iodide, what is obtained with potassium iodide? Yes, what is obtained with potassium iodide? Iodo benzene is obtained. Okay, iodobenzene is obtained. Then if you treat it with boron, okay, compounds of boron. So boron tetrafluoride is used here. Okay, now hydroboration is done here. Okay, so what is formed here? Fluorobenzene is formed. Again, one more reaction with copper powder plus HBr. If you treat copper powder with HBr, you obtain fluorobenzene. So first and second is what? The first and second, these are called as the Sandmeyer's reaction. Okay, so the starting product will be aniline. So aniline, you have to treat it with sodium nitrate. Okay, at 0 to 5 degrees Celsius in the presence of concentrated HCl, you have to this is converted into benzene diazonium salt. Okay, diazonium chloride. This, when you treat it with copper chloride, it will yield copper, that is chlorine, copper cuprous chloride, you will obtain chlorobenzene. If you treat it with cuprous bromide, you will obtain bromobenzene. So these first and second, okay, this first and second, what this you have obtained, it is a Sandmeyer's reaction. Then fourth one is a Ball-Chiman reaction. Fifth one is a Gatterman reaction. Okay. So in Sandmeyer's reaction, chlorine of copper cuprous chloride gets attached. So here this chlorine which is there, that will get attached to the benzene ring. Okay, in Gatterman reaction. So we'll solve some questions based on this. The reaction of toluene with chlorine in the presence of ferric chloride gives predominantly. Okay, what it gives? A, benzoyl chloride. B, metachlorotoluene. C, benzyl chloride. And D, orthoparachlorotoluene. Okay, I have got two answers as D. So the reaction of toluene. Okay, what is toluene now? What is toluene? Toluene is this. Okay, this you have to treat it with chlorine in the presence of FeCl3. What it gives predominantly? What you will get? You'll obtain ortho and para toluene. Okay, ortho and para toluene. So CH3 ortho and para. Okay, so this is ortho and para chlorotoluene. So D is the correct answer. Yes. Okay, so we'll go for the next one. Decomposition of benzene disonium chloride by using Cu2Cl2 in the presence of HCl to form chlorobenzene is. So what type of reaction it is? A, Sandmeyer's, B, Raschig's reaction, C, Cannizzaro, and D, Kolbe's reaction. Okay, I've got a one answer, that is A. What about others? And A is the right answer. Okay, so Sandmeyer's reaction is what? When you treat C6H5N2Cl, that is your benzene disonium chloride, in the presence of Cu2Cl2 and HCl. Okay, it forms C6H5Cl plus N2 gas is released. Okay, so this is a Sandmeyer's reaction. Next question. Friedel-Crafts reaction of bromobenzene. So I'll write the structure first, then we'll go for the reaction. So Friedel bromobenzene. So this is a bromobenzene. Yes. So we have to do Friedel-Craft reaction. Friedel-Craft is what? Alkylation. Okay, we are doing alkylation with methyl iodide. Okay, for alkylation, that is Friedel-Craft reaction, we use anhydrous AlCl3 as the reagent, and it undergoes a Friedel-Craft alkylation reaction. So what is the obtained? So what will happen? Your CH3 is the electrophile which will attack at ortho and para position. Where it will attack? It will attack at ortho and para position. So this is Br and this is CH3. Okay, so this is ortho and this is para. So which is the product obtained? It is C. I hope you are getting it. Yes. So these are the answer. The next one. So next we are going to see is the nucleophilic. So nucleophilic substitution in haloarenes. Okay, what is the nucleophilic substitution in haloarenes? So when chlorobenzene, okay, when chlorobenzene is reacted with NaOH, that is base. NaOH is what? NaOH is a base at 623 Kelvin and 300 atmospheric pressure. This Cl, okay, that is chlorine gas, chlorine atom will be replaced by OH. Okay, it forms phenol. What it forms? In chlorobenzene. Okay, so what is happening here? So I'll write the structure, you will understand it more clearly. So this is a chlorobenzene. So chlorobenzene, they are reacting it with what? NaOH. Okay, at the temperature of 623 Kelvin and 300 atmospheric pressure. So chlorobenzene is treated with this and you obtain what? This atom is replaced by OH. So this is what? This is a phenol. So it produces phenol and NaCl is the byproduct which is obtained. Okay. Another reaction, if you treat chlorobenzene with ammonia, if you treat chlorobenzene with ammonia, okay. If you treat chlorobenzene with ammonia, so I'll write here only. So if I treat it with ammonia now, chlorobenzene. Cu2O at 475 Kelvin and 60 atmospheric pressure, it forms aniline. Okay, how does aniline? This OH will be NH2. That is Cl will be converted or it is replaced by NH2 group. So it forms a aniline. Okay, it forms a aniline. Okay, so aniline is the product which is obtained. Okay, so like this is the reaction. So in haloarene, the nucleophile substitution reactions are difficult, okay, to carry out and hence it requires drastic conditions. So in haloarene, the nucleophilic substitution reaction is very difficult. Why? Because benzene, when you want to do a nucleophilic substitution reaction, benzene itself is a highly, what you can say, it is a good nucleophile. Okay, it is also a nucleophile, and if you want to attack nucleophile on nucleophile, so it will it is very difficult to carry out the reaction. Okay, so it requires very drastic conditions. So haloarenes, okay, they do not go nucleophilic substitution reaction. Then when an electron withdrawing group is present in ortho and para position, then the reactivity of halogens for nucleophilic substitution reactions will be more. Okay, the reaction, it increases. If there is a presence of electron withdrawing group at ortho and para position, then the reactivity of nucleophilic substitution reaction will increase. Okay, so this is the conditions for nucleophilic substitution reactions in your haloarenes. So next question, the compound that reacts fastest with sodium methoxide is, so which is the compound which reacts fastest with the sodium methoxide? So we know that electron withdrawing groups, okay, if there are electron withdrawing groups like NO2 group, okay, then what it will do, it will increase the reactivity of aryl halides towards the nucleophilic substitution reaction. And when it will be more, when it is present at ortho and para position. So option number C. Okay, if there is a electron withdrawing group, okay, electron withdrawing group is present and this electron withdrawing group is present at ortho and para position, then the reactivity conditions of aryl halides will be more. So option number C is the answer. Okay, just now we have discussed about this point, right? So we'll go for the next one. Chlorination of toluene in the presence of light and heat followed by treatment with aqueous KOH gives. So chlorination of toluene. So toluene, I'll write the structure of toluene. So this is the structure of toluene, CH3. So we are doing chlorination, that is Cl2 in the presence of light. Okay, what it forms? Light and heat. Okay, followed by treatment. So this should produce a product and this further is treated with KOH. Okay, so what is the product? This and this they have asked. Okay. Yes, try to solve this. So I'll write the product here. So if it undergo chlorination, it will form So what will happen? So there are three H atoms. So one of the hydrogen atom will be replaced by chlorine. So it forms CH2Cl. Now what will happen? Now if you are treating with KOH, okay, so this is a benzyl chloride. This is a benzyl chloride. Okay. Now this you are further treating with KOH. Now what is happening here? Now this Cl will be replaced by KOH. Okay, so OH. So it will be CH2OH. Okay, so this is a benzyl alcohol is obtained. So benzyl alcohol is obtained. Okay, so option number D. Option number D is the answer. I hope you have understood. So you have to just follow the okay steps, whatever is given, and then you can get the answer. I hope it is clear. Yes. So we'll go for the next one. Which of the following will give you yellow precipitate on shaking with aqueous solution of NaOH, followed by acidification with dilute HNO3 and addition of AgNO3 solution? Yes. So which of the following will give you a yellow precipitate on shaking with aqueous NaOH, followed by acidification? Okay, so the answer is C. Why? Because only iodine ion will react with silver nitrate. Okay, only iodine ion will react with silver nitrate solution and it gives a yellow color precipitate. Okay, only iodine reacts with silver nitrate solution to give you a yellow precipitate of AgI. Okay, now so here, when you are seeing A, we have chlorine and bromine. So this does not give any precipitate. Chlorine and bromine does not give any precipitate. Okay. Then in B, this also chlorine is present. It gives a white curdy precipitate. It gives a white curdy precipitate. And in this condition, okay, it does not give any precipitate. So which is given? It is C option. I hope it is clear. Okay, so only iodine will react, okay, with a silver nitrate solution and gives you yellow precipitate of AgI. What is Wurtz-Fittig reaction? As we have discussed earlier also, Wurtz-Fittig reaction is what? Okay, Wurtz-Fittig reaction, one alkyl group. This is a aryl group. Aryl halide is there. And one alkyl halide. Okay, alkyl halide. Alkyl halide. So when a molecule of aryl halide, one alkyl halide, when it reacts, it forms a alkyl aryl halide. Okay, alkyl aryl compound. Okay, alkyl aryl compound is formed. So like this. So I've explained this, okay, before in the methods of preparation. Then Fittig reaction. Wurtz reaction is what? It is between two molecules of alkyl halides. Fittig reaction is between two molecules of aryl halides. Okay. In the presence of dry ether, it forms biphenyl. Okay. These name reactions are very important name reactions. Okay. What is Grignard reagent? What is Grignard reagent? Grignard reagent means what? These are called as the alkyl or aryl magnesium halides. These are called as what? These are called as alkyl or aryl magnesium halides. Their general formula is given as RMgX. Okay. If different halogen atoms are present, then the ease of formation of Grignard reagent is iodine is greater than bromine, then chlorine, then fluorine. So if I take a bromobenzene and if I react with a metal that is magnesium, it forms phenyl magnesium bromide in the presence of dry ether. So this gives you me a organometallic compound. So here bromobenzene, okay, is treated with magnesium that is a metal in the presence of dry ether. It is giving you me a phenyl magnesium bromide that is a organometallic compound is obtained. Okay, so what is organometallic compound? Grignard reagents, that is RMgX. Okay, it is called as a organometallic compounds. So Grignard reagent is not prepared in aqueous medium, but it is prepared in ether medium. We have seen this question because the reagent reacts with water. So if Grignard reagent RMgX, okay, is treated with water, it forms alkene. Okay, it forms alkene. So because of that, what is done? It is prepared with it is prepared in ether. Okay. Next question. Which of the following can give a Grignard reagent when reacted with magnesium in dry ether? So which will react with uh, magnesium in dry ether and gives a Grignard reagent? You require a alkyl halide, right? Rx. Rx plus Mg will give you what? RMgX. So what is Rx? It is a alkyl halide. So it is a C6H5Cl, right? So when alkyl halide is treated with magnesium, that is a metal, uh, what it uh, what it forms? It forms a RMgX. So it is a B. B is the option. Okay. This is a cyano group. This is a alcohol group. Okay, and C2H6. So this is also what? This is a saturated hydrocarbon. So this is also wrong. Okay, it requires a alkyl halide. Okay, so option number B is the correct answer. So we'll go for the next one. In the following reaction, okay, C6H5CH2Br, if it is treated with Mg in the presence of ether and if it is undergoing hydrolysis, what is the product X obtained? Yes. What is the product X obtained? So if I do C6H5CH2Br and if I treat with Mg, what is the product obtained? It will form C6H5. Yes, C6H5, then MgBr. Okay, then further it is undergoing hydrolysis. Okay, first step it is reacting with this. Second step is reacting hydrolysis. Then it will form what? C6H5. Okay, C6H5 and this is will be converted into CH3. What is this? C6H5 CH3. So option number C is the correct answer. Yes. Yes. Nirmala, Sanjay, Nagratna. Yes, they have answered it right. Good. Okay. So option number C is the right one. Okay. So like this, you have to solve the particular questions. Next, chlorobenzene. Okay, I'll write the structure of chlorobenzene. So when chlorobenzene reacts with Mg in the presence of dry ether, it gives you a compound A. Okay, and further it reacts with ethanol to yield what? Okay, so we have to tell what is it yields. So first we'll write this reaction. So when benzene is treated with Mg in the presence of dry ether, it forms what? It forms, I'll write the structure. It forms MgCl. Okay, this is MgCl. This on further treatment with alcohol, what it forms? It forms benzene. Okay, it forms benzene. It forms C6H6. It forms C6H6. So that is benzene is obtained. So when you are treating it with alcohol, okay, it is forming C6H6. Yes, benzene is the correct answer. Okay, so we'll go for the next one. Okay, physical properties. Okay, just I'll give you idea about physical properties. So as the greater, so alkyl halides are being polar, they are insoluble in water as they cannot break hydrogen bonding already existing in water. As greater the molecular mass, stronger will be the van der Waals force of attraction and higher will be the melting point. On increasing branching, as the number of branching increasing, what will happen? The surface area will decrease and van der Waals force of attraction decreases and boiling point also decreases. Okay, so this is the thermal stability and density given us. So as if there is a single that is a chain system, okay, as the number of atoms are increases, okay, groups increases, the boiling point increases. But when the branching increases, then the boiling point decreases. So which of the following compounds has the highest boiling point among this? Yes, which will have the highest boiling point among this? If you have a chain, yes. Okay, Mohammed has answered it as B. Yes. So which will have a highest boiling point? Okay, so the answer is B, because you can see this is a straight chain compound. Here there are only 3 carbon atoms. Here one additional is there. Here there is branching. Here there is more branching. Okay. So because of this, B will be the correct answer. Okay. Last question. In the group of isomeric alkyl halides, the order of boiling point is, what is the order of boiling point? Primary. Okay, alkyl halides with branched and more spherical shapes have lower boiling point. Okay, as a result of their smaller surface area. So primary will be greater than secondary and then the tertiary. So option number D. Yes. Okay. Okay. So by this we have completed our chapter on haloalkanes and haloarenes. Okay. So I hope you have understood today's session. So we will start with the new chapter in the next class. Okay. So if any doubts are there, you can just add them in the chat box. Okay. So we can clarify it in the next class.